Так, оно же так должно работать, дальше просто надо включить доску.
Да, наверное, уже все. Нет, а это уже... Не, это я уже дальше не сделаю. Ну могу устроить. Вот, все правильно. Значит,
Покажите, где цифры. Где вот 1-1?
Я уже все стер.
Okay, the previous lecture we introduced the main ingredients of harmonic analysis on locally compact abelian groups. Namely, we introduced the dual group and defined the Fourier transform. Well, let's briefly recall the construction. So G is a locally compact abelian group. Always the abbreviation LCA will mean a locally compact abelian. G is a locally compact abelian group. For convenience, we assume that it is second countable. And we consider the group G hat all continuous unitary characters. That is, whole continuous homomorphisms from G to the circle. It is called the dual group of G. It is a group. It's also an abelian group under the usual pointwise multiplication. And it carries a canonical topology defined as follows. First, we consider the space C of G of all continuous functions on G. And we equip this space with the compact open topology. Well, G hat is a subset in C of G, and we simply take the induced topology on G hat. So it is called the contracted topology. So G hat is a group, and it becomes a topological space, and we prove that it's actually a topological group. That is, the multiplication, the group operation, and the inversion map are continuous. So it is a topological group, and we will see today that it is actually locally compact. Okay, now we define the Fourier transform for complex Rabel matters on G as follows. If nu is a complex Rabel matter on G, we define the Fourier transform of nu to be a function on the dual group given by the following formula. So we simply integrate chi, where chi is a character, with respect to nu. Sometimes we'll use the following short notation for the integral of chi with respect to nu. Although we proved that this function is bounded and continuous, f hat is a continuous bounded function of g hat, and its uniform norm, its uniform norm is less or equal to the norm of nu. So we obtain a bounded linear map F from the measure algebra to the algebra of bounded continuous functions, and takes every nu to the Fourier transform nu hat. This is a bounded linear map. And it is called the Fourier transform on M of G.
Excuse me, what's the norm on M of G?
The norm on M of G is we take the variation of nu and calculate the measure of G. So this is the norm on M of G. So this is the Fourier transform. This is the Fourier transform on G. Let's look at some properties of the Fourier transform. First of all, let's calculate something simple. Let's look at a simple example. example, let's take the Dirac measure delta x. The Dirac measure concentrated at x. If we calculate the Fourier transform, so the integral with respect to the Dirac measure is just the evaluation at x, we deduce that delta x hat I is just chi of x. That is the Fourier transform of the Dirac measure is the evaluation character epsilon x. Evaluation at x. Just like in the case of the Fourier transform of finite abelian groups, which was discussed at the first lecture. In particular, we see that if we substitute the identity of the group here, you see that the Fourier transform of the Dirac measure concentrated at the identity is the function which is identically 1. Let's recall that the Dirac measure concentrated at the identity is nothing but the identity element in M of G. So the Fourier transform takes the identity of this algebra to the identity of this algebra. And in fact, we can say something more interesting. The following proposition. The Fourier transform is a unital star algebra homomorphism. Unital star algebra homomorphism. Indeed, we already know that it is unital. Let's prove that it is multiplicative. So we take two measures, say nu1 and nu2. Let's take their so we must take the Fourier transform of their convolution. Evaluate at chi. So what is this? This is the integral of chi with respect to this measure, nu1, nu2. Let's now recall the definition of the convolution on the measure algebra. So this is nothing but the integral of delta chi with respect to the product measure, nu1, nu2. Where delta, let's recall that delta f of xy is f of x. It's just some substitute for co-multiplication on functions. Okay, so but chi is a character. So what is delta chi? Since chi is a character, we see that delta chi is nothing but chi tensor chi. This is chi of x, chi of y. And of course, if you integrate such a function with respect to the product measure, we just obtain the product of two integrals of chi with respect to nu1 and of chi with respect to nu2. In other words, this is nu1 hat evaluated at chi times nu2 hat evaluated at chi. And we see that our map is multiplicative. So it is an algebra homomorphism. Now we have to show that it is compatible with involution.
Sorry, what do we mean by tensor product of two functions?
Well, we have used this notation when we defined, when we discussed the measure algebra. Let's recall this notation. If we have two functions, in our case, they are continuous and bounded, f and g, two continuous bounded functions in our group. Then by the tensor product, we mean the following function on the product. or G by itself. This is just a notation. So by using this notation, we see that the tensor product, the algebraic tensor product of this space, this algebra by itself, is embedded into the space of continuous bounded functions on G cross G. This is an embedding. Of course, it is not surjective unless G is finite. It is not surjective, but it is an embedding. So in particular, we can consider elements of the algebraic tensor product, in particular, we can consider such simple tensors as elements of the space, as functions on the product. Okay, so now we have to show that this map is compatible with the involution. Let's take a new star and apply it to, we take the Fourier transform of this and apply it to chi. So what this is the integral of chi with respect to new star. Let's now recall the definition of the involution on M of G. So the definition was as follows. We must replace chi by S chi complex conjugate, integrate with respect to nu, and then take the complex conjugation here. This is just one of the two equivalent definitions of the involution on M of G. Well, but chi is a character. Well, maybe I have also to remind you the formula for S. So S is the map on CB of G, which takes every function f to the function f of x inverse. Okay, so but chi is a character. So if we substitute here chi, we get chi of x inverse, but chi is a unitary character. So chi of x inverse is just the complex conjugate of chi. So, and we take the complex conjugation again here. So this function here is just chi. In other words, this is a new hat of chi complex conjugate. And that's it. So the involution in CB of G is just the complex conjugation, the pointwise complex conjugation. And we see that the Fourier transform is compatible with the involution. So it is a star algebra move. Well, we're most interested in the restriction of this map of the Fourier transform to L1 of G. So let's choose once and for all the hard measure, on G. And let's recall that L1 of G, that's the L1 space with respect to the hard measure, is canonically embedded into M of G by means of the following map. And the L1 of G becomes a closed two-sided star ideal in M of G. So we can define the Fourier transform of an integrable function. To be the Fourier transform of the measure f mu. So explicitly, this is the function of the dual group given by the following formula. Okay, so our next goal will be, actually this is our main goal for today, is to construct a homomorphism between the dual group, between G hat and the maximal spectrum of L1 of G, in such a way that the Fourier transform on L1 of G becomes exactly the Gaussian transform of L1 of G. So this, in some sense, this result opens the door of applying Banach theory to harmonic analysis. So we start with the following construction. chi is a character of G, of the G group, we define map chi tilde of the measure algebra. As follows: chi tilde of nu is nu hat evaluated at chi. And let's observe that chi tilde is star character, unital star character of M of G. Well, because the Fourier transform is just the composition of two star homomorphisms, of two unital star homomorphisms. The Fourier transform, which takes nu to nu hat, and the evaluation character at chi, which is of course also a unital star character. So chi tilde is a unital star character of M of G. And let's also observe that the restriction of this character to L1 of G, chi tilde restricted to L1 of G, is also non-zero. It is non-zero because of the standard isomorphism between L infinity and the dual of L1. Indeed, if we assume that this restriction is trivial, then this integral would be zero for every little f in L1. But since this map is injective, chi would be zero in the zero element of L infinity, which is impossible because it is a unitary character. Its absolute value is everywhere one. So this restriction is not true. So we obtain a map noted by gamma, which acts from G hat to the space of to the character space of L1 of G. For typographical reasons, I write the hat here because otherwise it would be L1 of G is a little bit too wide to put a hat over this formula, so I put it on the right. So gamma acts from the dual group to the character space of L1 of G, and it takes every character chi to the character chi tilde restricted to L1 of G. So we already observed that this restriction is not trivial. And I claim, it's our first result for today, theorem 1, gamma is bijective. Theorem 2 will state that it is actually a homeomorphism. But first of all, we have to show that it is bijective. The proof will be divided into several lemmas. Lemma 1. Actually, lemma 1 is a very general result which holds for every locally compact group, not necessarily abelian. G is a locally compact group. And f is a function in L1 of G. I claim that the following map from G to L1 of G, which takes every point x in G to the left translate Lxf of f, is continuous. First of all, to prove this result, I claim that this result is true if f is continuous and compactly supported. It's true if f is continuous and compactly supported. And this is an exercise for you to prove the continuity of this map. And a hint is that essentially we have already proved this when we discussed the uniqueness of the Higher measure. Before, well, formally we almost proved this before, because formally I didn't put this result in this concrete form. What we actually proved is that the integral of this function with respect to an arbitrary positive Radon measure is continuous, depends continuously on x. But if you look at the proof, you will see that actually the proof shows that this map itself is continuous. So I won't repeat this argument because it is identical to what we did when we discussed the uniqueness of the Higher measure. So this is true if f is continuous and compactly supported. What happens if f is just integrable? Well, let f be an integrable function. Take a positive epsilon. Let's choose continuous compactly supported function g such that it is close to f. So we know that this subspace is dense in L1 of G. So we approximate f by the continuous compactly supported function. And if you take now two points, x and y, in G, so we want to show that, first of all, we know that this map is continuous if we replace f by G. Well, it's not. First of all, we choose a point x, only one point x in G, and we know that there is a neighborhood u x, such that for every y in U, the following number, Lxg minus Lyg, is less than epsilon. Because this map is continuous with f replaced by G. Even though I replace here f by G, then we get the following estimate: Lxf minus Lyf is less than or equal to Lx applied to f minus G plus Lxg minus Lyg plus Ly applied to G minus f. But the left translate is isometric, so we, of course, everywhere we take the L1 norm. The left translate is isometric on the 1 because the Higher measure is left invariant. So this is just the norm of f minus g, and the norm of f minus g is less than epsilon, so this is less than epsilon. For the same reason, this is less than epsilon, and this is also less than epsilon by the previous line, assuming that y sits in U. So we see that this is less than 3 epsilon, and it shows that our map is indeed continuous. Okay, now lemma 2 is a simple but useful result of all Banach algebras. Lemma 2. Suppose that A is a commutative Banach algebra. And I is a closed ideal. Okay. And let's denote by A hat I the set of those characters A such that the restriction of chi to I is not trivial. This is a subset in the character space of A. I claim that this is an open subset. A hat I is an open subset of the character space. And the restriction map, which acts from this set to the character space of I, as denoted by alpha, it takes every character of this form to its restriction to I. So I claim that this map is homeomorphism. Well, indeed, why is it homomorphism? Well, first let's prove that it is injective. Indeed, if we take a character of A, which doesn't vanish I, then for every B in I, we have the following formula. Let's denote a restriction of chi to I by phi. So we have the following formula: chi of A is phi of AB, or phi of B, whenever phi of B is non-zero. Well, this is more or less immediate, because if since chi extends phi, if I substitute replace here phi by chi, so here we have chi of A, chi of B divided by chi of B, which is of course chi of A. So this is trivial, but this is convenient, because this formula really shows that alpha is injective. That's denoted by star. So this formula implies that alpha is injective. Well, indeed, chi is uniquely determined by phi. We can fix an element B such that phi of B is non-trivial, and reconstruct chi from phi by using this formula. So alpha is injective. Why is it surjective? Well, again, this formula hints how to construct the inverse map. Indeed, let now phi be a character of I. Let's choose an element B in I such that phi of B equals 1 for convenience. We can always find such an element because phi is a non-trivial character. And define chi. Define chi from A to the complex numbers. As follows: phi of A is phi of A B. Well, this is essentially the only candidate because of this formula. This is the only candidate for the pre-image of phi under this map. We have to show that it is a character. Well, this is an explicit calculation. Phi of A1, A2. Well, maybe it's better to start from the opposite side. Chi of A1 multiplied by chi of A2. This is phi of A1B, phi of A2B. Phi is a character, so this is phi applied to A1B, A2B. The algebra is commutative, so we can put it in the following form: phi of A1, A2B times phi of B. Again, we use the fact that phi is a character. This is 1. This is 1. And this is chi of A1, A2. Okay, so chi is a character. A. And it clearly extends phi because of this formula. If A sits in I, then phi of AB can be written as phi of A times phi of B, which is just phi of A. Okay, so we see that alpha is bijective. Now, an exercise for you is to complete the proof. Show that A at I is open, and both alpha and alpha inverse are continuous. Actually, the first two statements are almost immediate. This one is easily follows from the definition of the weak star topology, and the continuity of alpha is also immediate from the definition of the weak star topology. Alpha is just the restriction map. Which is not entirely immediate is the continuity of alpha inverse, but the continuity of alpha inverse can be deduced from this formula. formula star. This is a hint to use formula star for the continuity of alpha inverse. Well, actually, what we actually need is that alpha is bijective. This is the most essential part of this lemma. Well, from now on, G will be again a locally compact Billion group. So we are going to apply lemma 2 in the following specific situation where A is the measure algebra and the ideal I is L1 of G. So we identify L1 of G with an ideal of M of G in the standard way by using the standard embedding of L1 of G into M of G. Well, let's look at the following picture. So we have the following three objects: the dual of G, the dual group. Set A hat I of those characters of the measure algebra which don't vanish on the L1 of G, and we have the character space for L1 of G. And we have two maps here. This is our map alpha from the previous lemma. And this map beta takes every unitary character of G to the character chi tilde, which was defined some time ago. So we already know that it doesn't vanish on L1 of G. So it indeed fits in this space. Well, clearly the composition alpha beta is our map gamma. Alpha beta is gamma. Lemma 3. Beta is bijective.
Sorry, gamma is an actual, like, what is the structure on the L1 of G and the G hat that we like? Is it just we use their topological spaces and we assume gamma to be the map of topological spaces, or?
At this point, we actually don't use the topology. So we want to prove theorem 1, which we are trying to prove, states only that gamma is bijective. So we will prove later that it is a homomorphism. But at this point, gamma is just a map between two sets, G hat and I hat.
Okay.
It will be a homomorphism, but this will be our next result. So now we are trying to prove that it is bijective. Okay, so we already know that alpha is bijective. So if we prove that beta is bijective, then of course we'll prove theorem 1. Okay. First of all, let's observe that for every character chi of G, chi can be reconstructed from chi tilde. So let's recall that chi tilde is chi tilde is given by the following formula. So let's now observe that chi can be reconstructed from chi tilde as follows. It's just chi tilde evaluated at delta x. And this already implies that beta is injective. And at the same time, the same formula hints how we can prove that it is surjective. We take now an arbitrary character of A which doesn't vanish at I, that's denoted by phi. Then define a function phi on G as follows. Phi of x will be phi applied to delta x. Well, indeed, if we want to find the pre-image of phi here, this formula shows that the only candidate is given by this formula. So we now have to show that chi is a unitary character and that chi tilde equals phi. The easiest task is to show that it is multiplicative. Well, this is trivial because phi was a character. And the delta xy is, of course, the product, the convolution of delta x and delta y. And so we obtain phi of x times phi of y. Because phi was a character. So chi is multiplicative. Also, it takes the identity to 1. Phi of E is 1, because phi is a unital character. And this implies that chi is non-zero, because, well, chi of x inverse by the multiplicativity is chi of E, which is 1. So chi of x is non-zero for every x. So we obtain a character at this point in the purely algebraic sense. That is a character of G, a multiplicative map from G to C cross, to the group of non-zero complex numbers. We want to show that it is continuous and unitary. Well, why is it unitary? The absolute value of chi of x. Let's look at this formula. Phi is a character of a measure algebra. We know that the norm of every character of a Banach algebra is at most 1. So it is dominated by the norm of delta x, but the norm of delta x is, of course, 1. So the absolute value of chi of x is less than or equal to 1 for every x. And so this implies that the same is true for x inverse. But again, chi is a character, so this is 1 over chi of x. And, these two inequalities together imply that chi of x, the absolute value is 1. So it is a unitary character. Why is it continuous? Here it is essential that phi doesn't vanish at I. So far, phi could be an arbitrary character of the measure algebra. And this construction here shows that any character of the measure algebra yields a unitary character of G. But in general, it is not continuous. But I have to show that it is continuous provided that phi doesn't vanish on L1 of G. Well, indeed, it doesn't vanish on L1 of G, so we can always find a function, let's denote it by h, in L1 of G, such that phi of h equals 1. Then chi of x can be written as follows. Chi of x is phi of delta x, phi of h. But phi is a character, so this is phi applied to delta x convolved with h. And the convolution of the Dirac measure with the function is just the left translate. Phi applied to the left translate of h. And let's now recall lemma 1. Lemma 1. Lemma 1. The map which takes x to LXH is continuous. And here we simply compose this map with phi. Phi is also continuous. So this implies that chi is continuous by lemma 1. And so in summary, we see that chi is indeed a continuous unitary character of G, that is, it is an element of the dual group. So to complete the proof of lemma 3, we want to show that chi tilde equals phi. This is not entirely immediate because by construction they agree on the Dirac measures. But of course, the measure algebra is not spanned by the Dirac measures. And actually, the closure of the linear span of the Dirac measures is not dense in M of G. So some extra argument is needed to show that they agree everywhere. But we already know that alpha, this map, we already know that alpha is bijective. This was lemma 2 or lemma 2. Lemma 2 was that alpha is bijective. So to prove that these characters are the same, it suffices to show that they agree on I. So by lemma 1, we see that to show that they agree on a 1, phi tilde of f equals phi of f for every f in a 1 of G. Well, why is it so? Well, first of all, phi restricted to a 1 of G is a continuous linear function, of course. And by the standard duality between L1 star, between L1 and L infinity, we see that phi is given by integration of this, so it comes from a function in L infinity of G. So there is a function of G in L infinity of G, L infinity of G, such that phi of f is the integral of the product of G for every f normal. Okay, now let's write it in a slightly different way. So phi of f is phi of f times phi of h, where h is our function satisfying this condition. Phi of h is 1. Phi is a character, so this is equal to the phi applied to the convolution of f and h. And we substitute it here and see that this is the integral of the product f star h, f star g times f star h times g. Well, let's write this explicitly. This is so the convolution evaluated at x is being given by the following integral f of y, h of y inverse x. So we integrate this with respect to u, then multiply by g, and integrate with respect to x. With respect to y, and then with respect to x. Okay, now we see an iterated integral. When we see an iterated integral, we always want to interchange the order of integration by using Fourier's theorem. Clearly, it applies here because the g is bounded and this function is integrable. So as a result, we see that this is equal to the following: f of y is multiplied by the integral of this is the left translate of h with respect by y. So this is L y h evaluated at x times g of x, g mu of x, g mu of y. So let's now look at this integral. What's this? Well, we compare this formula and this formula and see that this is nothing but phi applied to LYH. Phi of LYH. But LYH is the convolution of the Dirac measure delta y and h. And phi is a character, so this is phi of delta y, phi of h. But phi of h is 1, and phi of delta y is just chi of 1. So this was our definition of chi. So we see that this is just chi of y. And as a result, the whole expression is the integral of f of y 1 G mu, which is nothing but chi tilde related to. Okay, so we see that phi and chi tilde agree on L1 of G. And by this observation, this implies that they are the same everywhere. And so beta is vacant. This concludes the proof of lemma 3. Now combining lemmas 2 and 3, we obtain our theorem 1. Our theorem 1 follows from lemma 2 and lemma 3. Let's look once again at this picture. So lemma 2 shows that alpha is bijective, and lemma 3 shows that beta is bijective. So as a result, gamma is also bijective.
Could you repeat once again why the continuity of some map in lemma 1 implies that we only need to show that these two things coincide on L1 of G?
So they coincide on L1 of G just by explicit calculation.
Yeah, but why is it enough?
It's enough because, well, let's look at once again. So they are elements in this set.
Yeah.
Both chi tilde and phi, they sit in here. And alpha is, we already know that alpha is a bijection. Alpha is bijection. Alpha is just the restriction map. Alpha of psi is psi restricted to alpha is just the restriction map. So to show that two characters in here are the same, it's enough to show that they are the same on R. And this is exactly what we prove here.
It follows not from lemma 1, but from lemma 2. It's in this part here.
Yeah, sorry?
It follows from lemma 2. It's written lemma 1. I think that was concerned.
Thank you. This is not lemma 1, but lemma 2. Thank you. Thank you. Lemma 2. Of course, the bijectivity of alpha was lemma 2. Right. Lemma 1 was used here when we put the continuity of chi at this place. Okay, so now we see that gamma is bijective, and by the way, this implies the following important corollary. Oh, here. The corollary is that L1 of G is Hermitian. Why is it so? Well, we already know that every character of L1 of G comes from a unitary character of G. But on the other hand, by construction, for every unitary character chi of G, the character chi tilde is not just a character, it's a star character. It's a star character of L1 of G. And since we have just proved that every character of L1 of G is of this form, we deduce that all characters of L1 of G are star characters. All characters of L1 of G are star characters. But this is one of the equivalent characterizations of commutative Hermitian Banach star algebras. So we proved at the previous lecture that a commutative Banach star algebra is Hermitian, that is the spectrum of every self-adjoint element is real, if and only if all characters are star characters. So this implies that L1 of G is Hermitian. Okay. So as I proved before, now our task is to prove that gamma is actually a homeomorphism. Theorem 2. Gamma is a homeomorphism between G hat, where G hat is equipped with the Pontryagin topology, and the character space of L1 of G, which is by default equipped with the Gelfand topology. Again, the proof will be divided into several lemmas. The easiest part here is to prove that gamma is continuous. Gamma is continuous. This is very easy because of the characteristic property of the weak star topology. Well, that is equivalent with the weak star topology. And to prove the continuity of gamma, it's suffices to show that the map which takes chi to chi tilde evaluated at f is continuous for every f in L1, just by the properties of the weak star topology. But what is chi tilde of f? Let's recall that the chi tilde of f is the Fourier transform of f evaluated at chi. But the Fourier transform is a continuous function. This was proved at the previous lecture. Oh, this is true. Okay, so it is continuous. The next step is, next lemma is the following purely functional analytic result. If we take an arbitrary normed space, E is a normed space, and suppose that we have a bounded subset of the dual, B is a bounded subset of the dual of E star. Then I claim that if we equip B with the weak star topology, then the pairing between B and E is continuous. So this map takes each pair Fx to F is continuous. By the way, for unbounded B, this is not true. It's used to exercise function in functional analysis to show that if B is not bounded, then lemma fails. The bound is essential here. Well, since it is bounded, let's denote by C the supremum of the norms of functionals in B. Let's take two elements F and F0 in B and two vectors X and X0 in E. And let's do the following simple calculation. F of x minus F0 evaluated at X0. So we want to show that for every positive epsilon, we can find two neighborhoods, a neighborhood of F0 and the neighborhood of X0, such that if F and X sit in the respective neighborhoods, then this number is less than epsilon. And this is a simple application of the triangle inequality. So this can be estimated as F applied to X minus X0 plus F0 minus F0 of X0. The first sum can be estimated as C times the norm, X minus X0, because the norm of F is less than or equal to C. And the second summand is nothing but one of the standard semi-norms generating the weak star topology on a star. This is the semi-norm corresponding to X0. Well, basically, this concludes the proof, because if now we choose F in the neighborhood of F0 consisting of those F for which this is less than epsilon divided by 2, and if the distance between X and X0 and is less than epsilon over 2C, then the sum will be less than epsilon. Okay. Before we state the next lemma, let's introduce some temporary notation. by G hat W, we denote the dual group G, but not with the canonical topology, not with the conjugate topology, but with the Gelfand topology. Gelfand topology induced from L1 of G hat, from the character space of L1 of G. We already have a standard bijection between G hat and L1 of G hat, so we simply move the Gelfand topology from this space to G hat. Of course, if theorem 2 is true, then this topology will be identical to the Petrarchan topology, but the theorem 2 is not proved yet. So we must be careful here, and we denote the space by G hat W. Lemma 3 states that the pairing between G hat W and G, so it takes the product of these two spaces to the circle for every pair chi and x goes to chi of x. So this map is continuous. To prove the continuity of this map, let's first do a little calculation. Let's take a character chi of G, a function f, the one of G, and a point x in G. And let's observe that if we apply the character chi tilde to the left translate of f, Lxf, this can be calculated as follows. So the left translate of f is the convolution of the Dirac measure delta x and f. And the chi is a character, so chi tilde is a character, so this is chi tilde of x times chi tilde of f. But sorry, chi tilde, not chi tilde, just chi of x. Chi of x, because chi of x is chi tilde of delta x. Chi tilde of delta x equals chi of x. So we get this formula. And if f is chosen in such a way that the second number is non-zero, we deduce that chi of x can be calculated as follows. That is chi tilde applied to Lxf over chi tilde of f, provided that this number is non-zero. If chi tilde of f is non-zero. Now let's apply this calculation to lemma 3. Let's choose a character. Take a character chi 0 in G, and choose the function f such that chi tilde chi 0 tilde of f is non-zero. F of 1 of G such that chi tilde 0 of f is non-zero. So again, by the definition of the weak star topology, we see that if we replace here chi 0 tilde by a character in a small neighborhood of chi 0, then this number is non-zero. So there is a neighborhood U of chi 0 in G hat with respect to the Gelfand topology, such that for every chi in U, chi tilde of f is non-zero. If we just take the respective standard neighborhood, standard weak star neighborhood of f of x of chi 0 corresponding to f. This is the approach of the pointwise convergence, so such neighborhood always exists. Well, now if we look again at this formula, so it makes sense for all chi in U. We see that to prove the continuity of our map, which takes the pair chi and x to chi of x, it's actually suffices to prove the continuity of the following map. It suffices to show that the map from U times G to complex numbers, which takes pi x to pi tilde LXF, is continuous. Because if it is continuous, then the numerator here is continuous. The denominator also is continuous because it's just a special case. We can substitute the identity here. And so the whole function is continuous. This one is, and this one are continuous. So this will imply that this map is continuous on its restriction to U cross G is continuous, but since U was an arbitrary open neighborhood of a suitable open neighborhood of an arbitrary point, so we see that the map is locally continuous, so it is continuous. Okay, well, and to prove that this map is continuous, we apply lemma 2 to the following situation. So U cross G is mapped to L1 of G hat cross L1 of G by the following formula. Chi x goes to chi tilde LXF. So what can we say about this map? We can say that it is continuous. Well, indeed, U is equipped with the topology induced from L1 of G hat, so it is just an embedding by the first coordinate, and by the second coordinate it takes x to LXF. But it was one of our previous lemmas. This was lemma 1 in theorem 1. Lemma 1 in theorem 1 shows that the map which takes x to LXF is continuous. So this one is also continuous. Okay, so this is continuous, and here we just take the pairing between this is a subset of the dual of L1 of G. So this pairing takes f x with terms of notation I f to phi 1. And it is continuous by lemma 2. This is a bounded subset of the dual equipped with the weak star topology. So if we look at lemma 2, so B is the character space of L1 of G, and E is L1 of G. Lemma 2 applies. Okay, so now of course the superposition, the composition of these maps is exactly what we want to prove. So this one is continuous. Okay, so this completes the proof for lemma 3. Lemma 4 was proved some time ago. Let me just recall the statement. It's useful lemma in general topology. You have three topological spaces, x, y, and z. Arbitrary topological spaces. If we have some results about arbitrary topological spaces, then this result must be true or false. But this one, in this case, it is true. So it is true. It is true because it is a result about arbitrary topological spaces without any extra conditions. So three topological spaces and a continuous map f from x cross y to z. And suppose we have an open subset z0 in z and a compact subset y0 in y. Then the set of those points in X for which f of xy belongs to z0 for every y in y0. This subset is open in X. So roughly this means that the intersection of compactly many open sets is open. We have already proved this lemma before, and we used it when we discussed the hard measure. Now we will use it again. Lemma 5, which is the final step in theorem 2, states that gamma is an open map. This will complete the proof of lemma of theorem 2 because the gamma, we already know that gamma is bijective and continuous. So if we prove that it is open, then it will be a homeomorphism. So why is it open? Let's take a character chi G, and let's take a basic open neighborhood of chi, which corresponds to a compact subset K of G, and a positive epsilon. So the basic open neighborhood of chi, UK epsilon of chi, consists of those characters phi, for which phi of x minus chi of x is less than epsilon for all x in K. So this is a basic open neighborhood of chi. Okay, so we want to show that gamma takes this neighborhood to an open subset of the character space. So we know that well, basically we have to show that it is open in we have to show that it is open in G hat W, right? We want to show that the set is open in G hat W. But we know lemma 3, was it lemma 3? Yeah, this was lemma 3. Lemma 3 implies that the map which takes phi and x to phi of x is continuous. So therefore, the map which takes a pair phi and x to phi of x minus chi of x is also continuous on G hat W times G. And now we apply lemma 4 to this function on this product. Well, X runs over a compact set K. K is compact. So this is a preimage of epsilon neighborhood on the real line. So Z0 is just the interval from minus epsilon to epsilon, and lemma 2 implies that the set is open. In G hat W. Okay, so this completes the proof of lemma 5. And lemma 5 together with lemma 1. Imply theorem 2. Now theorem 2 follows from lemma 1 and lemma 5. So we have a homomorphism between G hat and the character space of One of G. So and as a corollary, we see that G hat is locally compact. Simply because it is homomorphic to the character space of One of G, and the character space is always locally compact. And finally, this will be very easy. We can identify the Fourier transform on G with the Gelfand transform on One of G. Theorem 3 states that, first of all, that the Fourier transform takes One of G actually to C0 on G hat. So far, we knew only that it takes it to CV of G hat, to the space of continuous bounded functions. So this is a kind of the Riemann-Lebesgue lemma in the abstract setting, which states that the Fourier transform of integrable function vanishes at infinity. So it vanishes at infinity, and moreover, the following diagram commutes. Following diagram commutes. This is L1 of G. So this is the Fourier transform, which takes L1 of G to C0 of G hat. The Fourier transform. Here we have C0 of the maximal spectrum. That is on L1 of G hat. One transform due to gamma. And we have the map gamma dot, which is induced by the homomorphism gamma between G hat and L1 of G hat. So this diagram commutes. Gamma dot is an isometric star isomorphism because gamma is a homomorphism. So basically, this means that the Fourier transform and the Gelfand transform on L1 of G are essentially the same object. In fact, it suffices to prove that the diagram is commutative, because if it is commutative, then of course the Fourier transform takes L1 of G to C0 of G hat. And this is just an explicit calculation for every f in L1 of G. So we apply gamma to f, and then apply gamma, little gamma dot, apply to the Gelfand transform of f, and then so this will be a function on G hat. So we evaluate at chi, where chi is a character of G. So what is this? Gamma dot takes every function in here to its composition with gamma, little gamma. Sorry, we have big gamma and little gamma. So we have to compose this function and little gamma. Then we apply little gamma to chi and get chi tilde. And big gamma of f is just f hat. Oh, sorry, this is not. This is not entirely correct. So gamma of chi is chi tilde. Yeah, of course. Gamma f, not the Fourier transform, gamma f, the Gelfand transform of f. We have the same notation for the Fourier transform and for the Gelfand transform. This is not a coincidence, of course, because they are essentially the same. But here let's avoid using the hat because it is a bit ambiguous. So the Gelfand transform of f must be applied to little gamma of f, little gamma of chi. That is to chi tilde. And by the definition of the Lagrange transform, this is chi tilde applied to F. And chi tilde applied to F is again by definition the Fourier transform of F applied to chi. And that's it. This shows that the composition of these two arrows is just the Fourier transform. Okay, so this completes the proof. And our final corollary for today is that is the density theorem for the Fourier transform, which states that the free image of L1 of G is dense in C0 of G. So some time ago, we proved this for some concrete groups, the integers, the circle, the real line. Now we see that this is true for any locally compact abelian group. And it is dense because L1 of G is a Hermitian. We already know that L1 of G is Hermitian. And in the previous lecture, we proved that the Gelfand, the image of the Gelfand transform of every Hermitian Banach star algebra is dense. So now we can identify the Gelfand transform and the Fourier transform. We see that the image of the Fourier transform is dense. Okay, so that's all for today. As the next lecture, we prove the uniqueness theorem for the Fourier transform, which states that the Fourier transform is injective on L1 of G. And then we discuss positive functionals, the genus construction, and apply this construction to functions of positive type on locally compact abelian groups, and to an important Bochner's theorem, which characterizes functions of positive types of positive type in terms of measures of the G group.
А вот требования либидо мы это понятно, да?
Ну, раз диаграмма коммутативна, ну, смотрите, просто вот эта штука отображается ценой в ценой. Она же, ну, гомеоморфизмом порождена. Значит, это порождается ценой в ценой, поэтому если композиция этих двух совпадает с этим, то у этих двух то образ лежит ценой.
Да.
Как-никак, поэтому все это вот можно. Поэтому просто, ну, коммутативный диаграмм проверили, и отсюда учиться.
Как из геометрии следует плотностью образа?
Один раз просто доказали. Вот у нас была теорема на прошлой лекции, что если у вас есть Эрмитова Банахова звездочка алгебра, то, ну, там опять была факторизация, она Эрмитов подает только тогда, когда все характеры уложат конволюцию. И отсюда, в частности, следует, что образ Гельфандовский образ плотен. Ну, мы термин вспомнили штраф в случае применения.
Гельфандовский.
Да, Гельфандовский.
Да.
Ну, а Гельфандовский и Хурьевский, они одинаковые. Это же изометрический изоморфизм, поэтому у этого плотный образ, до этого такой довольно плотный.
Коммутативность нужна как раз, чтобы для преобразования Гельфанда, чтобы она была изоморфизмом. Когда L1 будет коммутативный Банах.
Нет, один он и так коммутативный.
Нет. Ну да, я про это говорю, в смысле, сейчас вот коммутативность группы как раз вот в этом, да?
Ну да, конечно, ну, мы многие пользуются коммутативностью, можно проследить там, по доказательству. Здесь, да, ну здесь, конечно, коммутативность здесь долго, ну, просто было бессмысленно. При коммутативном случае преобразование по-другому определяется. Там надо вместо групп характера брать множество классов вариантов неприводимых представлений. Тогда будет что-то интересно. Потому что если группу не делать, вообще этого характера может быть очень мало, а может вообще не быть, это реально. Нет, мы говорим еще про личность. Но, в общем, характер может быть очень мало. Можно, например, группа характера только один, здесь, наверное, единица. Так что для неактивных групп там и преобразование Фурье, собственно, по-другому определяется, там много по-другому делается. Здесь, конечно, важно. Ну,